All right. Good afternoon, good evening, or good morning, depending on when you're watching this. So today, what I would like to do is to spend a little bit of time talking about the mole and molar mass, just to give you some background on it. Again, if you want more videos on this topic, they're already posted in the Blackboard. The links are there. But this will give you a little bit more, or you could use this as an introduction. And then if you feel like you need it, you could work with the other ones that are already produced. So I'm going to talk about the mole and molar mass here. Now, the mole and molar mass are in section 3.4. Okay, so let me give you a little bit of background on it. The idea here is that once chemists realized that there were these very small particles like the atom or the molecule, they realized very quickly that they're so small that you can't see them, but there must be large numbers of them, right? There must be huge numbers of atoms and molecules. And of course, we know that that's true today. So they needed a way to kind of quantify how much substance you have. And they called that the mole, M-O-L-E. The word mole is derived from the root of like molecule, right? So the two are connected, but they're not the same thing. A molecule is the smallest unit of a substance that has particular chemical and physical properties. So for example, yesterday we talked about oxygen, right? So oxygen is a diatomic element. So it's O2. So if you combine two oxygen atoms, you get a molecule, right? So that's called a molecule of oxygen. Okay. Each of the little individual balls there are atoms, right? Now, they actually didn't have a good physical picture of what was happening back when they came up with the idea of the mole, but we do now. So if you take two oxygen atoms, you have a molecule of oxygen. Now, phosphorus is actually interesting too. Typically, we're going to ignore this fact about phosphorus, but phosphorus is an element that is found in the earth. It is used in matches. So when you strike a match, it's mostly sulfur, but there's a little bit of phosphorus in there. Phosphorus burns in oxygen really well, so it makes a good match. And phosphorus actually has, let's not put the symbols. It's actually made of 4 different atoms. Okay, I'll put a P in there just so you know that's a phosphorus. Okay. So this is a molecule of phosphorus. It's an unusual material. There aren't many substances where there's 4 atoms, right? Phosphorus is the only one I know. And then this similarly, sulfur is interesting in that it makes in its natural state, sometimes, I don't want to say always, it makes a ring of 8. Okay, I'm not drawing these too well. I'm gonna have to close the loop a little bit here. 1, 2, 3, 4, 5, 6, 7, 8. There we go. So it's actually S8, right? It's actually S8. Phosphorus is actually P4, and this would be a molecule of sulfur. Now, very often we ignore that when we do problems. Sometimes you'll see it out there. There are problems you'll see in textbooks and such where it's S8 or it's P4, but typically we have the diatomic elements like oxygen, hydrogen, and nitrogen. But the other ones, we just sort of write the symbols of the element. We don't take into account that they are actually made up of molecules. And if you want to look at carbon, carbon's a fascinating element. There is actually there is actually a molecule of carbon that has 60 atoms, and they're shaped like a soccer ball. I'm not even gonna bother to try to draw it, but they actually call it Minster fullerene, or for short, you're much more likely these days to see buckyball or buckyballs, C60. So they look like little soccer balls. They're hollow on the inside, and these 60 carbon atoms make a shell around nothing. It's a vacuum on the inside. There's nothing in there. You can do little processes where you put an atom on the inside, like maybe an iron atom or a gold atom, that sort of thing. But those are called buckyballs after a famous architect, Buckminster Fullerene. And it turns out upon investigation, there's other ones as well. There's something called C70. So that one is also a buckyball. It's also like a soccer ball, but it's a little different shape, and there's 70 atoms in there. So those are big molecules, right? And so the molecule is like the smallest unit of a substance that has particular properties. So, an O2 molecule has a particular chemical property that's different from an oxygen atom. So if you converted O2 into 2O, and what does that mean when you say 2O? That means you got two separate atoms. They're separate. This is atomic oxygen. You've got actual individual atoms, right? Those individual atoms would behave chemically differently from O2, right? So individual oxygen atoms are different than oxygen molecules, okay? So this is sometimes called molecular oxygen. I'll write over here, molecular versus atomic oxygen. And the British actually, they do something very clever. They actually put the 2 in there, and they call it dioxygen or dinitrogen to tell you, oh, we're not talking about atomic oxygen or nitrogen. We're talking about molecular oxygen or nitrogen, okay? So let's come back then. What is the mole? I'm going to give you a little bit of a background on what the mole is. Okay. It is perhaps the greatest cause of confusion among science students that exists. Well, one of them anyways. In chemistry, it certainly is. So the mole can be thought of in a couple of different ways. One way, one interpretation, is that we talked about this when we did the percent composition. We have this number for hydrogen, which we call the atomic mass. Okay, 1.00794, we call that the atomic mass. Okay, and what that means is one atom of hydrogen. So I'm just going to write one atom H, one atom of hydrogen. And I'm going to put an equal sign. This may seem awkward to you, but that's how we generally do it. Equals 1.00794 AMU. And that AMU is the units. Remember, when you're measuring something, you got to have units most of the time. So if I'm measuring the temperature outside, I could say it's 70. And you would say 70 what? I'd say 70 degrees. And then you'd say, well, wait a minute. I've taken science and chemistry, and I recognize that there's different temperature scales. So when you say 70 degrees, do you mean 70 degrees Fahrenheit? Do you mean 70 degrees Celsius? Do you mean 70 Kelvin? Do you mean whatever? There's several different temperature scales that you can use. So AMU is the unit of measure of the mass, and it's a really small number. An AMU, really what it's called is an atomic mass unit, AMU, right? And just for full disclosure here, this is actually an outdated term. It's an outdated unit, and actual working physicists and engineers that are studying the masses of elements, they would actually say it's not an AMU. They would say it's a unit. But we don't need to worry about that. We're just going to call it atomic mass units like your textbook does. It's just a little dated now, but that's still what we call it in general. So an AMU is an atomic mass unit. It's a really small number. Atoms are small, so a hydrogen atom doesn't have very much weight. Okay, it doesn't have much mass. So we might ask, suppose we had a really large number of these hydrogen atoms, how much would they weigh together collectively, right? And the answer is a lot more, right? If you have a lot of atoms, they're going to weigh a lot more. So it becomes more useful to use a unit that's more practical. So if you worked in a laboratory, in a chemistry or biology laboratory or physics laboratory, you will recognize that it's very common to use the unit of grams, right? There's another unit of mass called the gram, G-R-A-M, and the abbreviation is a G, right? Now we can use prefixes as well, centigrams, kilograms, what have you. But let's just talk about the gram for right now. Suppose I said this. This is what I'm going to do. I'm going to count out a large collection of these hydrogen atoms, a huge number of them. Okay, I'm not going to fill up this balloon, but I'm just going to put a lot in there. And suppose I put in exactly the right amount of hydrogen atoms such that the mass of those atoms collectively, all together, was this number right here, but in the units of grams. Okay, so you see what I did? I arbitrarily said I want to have a mass that's exactly the same number I've been using all along, 1.00794. But I'm going to have so many atoms that collectively their mass is 1.00794 grams. Now that's significant because that's something I can handle experimentally, even in a kitchen. A kitchen scale generally has the ability to measure the mass of something to about 1/10 of a gram, 1.0 grams, maybe, clearly not 1.00794. But it could wait out to 1.0 and tell the difference between 1.0 and 1.1. If I had a little bit nicer balance, I could go out to 1.01. And if I had a nicer one, I could go out to 1.008. See how it's becoming more precise? A really, really nice balance, one that costs a few $1,000s, would be able to weigh out something that's pretty much 1.00794, and it would be in grams. Okay. Now, the significance of that, or the reasoning behind that, is I want to weigh things that I can weigh with a balance. I can't weigh an AMU. I mean, we have machines called mass spectrometers that can do that, but they cost tens of thousands or hundreds of thousands of dollars, and they are, not needed for the everyday weighing of, say, an aspirin tablet or ibuprofen or a piece of iron, right? We don't weigh those kinds of things using a mass spectrometer. We weigh like 1 or 2 or a few thousand atoms that way. So we want to keep the same number that we have in the periodic table, 1.00794, but we want to have units that are practical to measure. So it turns out there's some number of these where that's going to work. Right? You just add up the mass of all of them together. At some point, if you just keep atom by atom, or thousands of atoms by thousands of atoms, eventually your balance will say, oh, it's 1.00794. You would match it up with this number over here on the left. I haven't told you how they get that number in AMU. That's a sidebar that would take some time, but suffice it to say we can do that. But we would eventually get this number here, and there's going to be some number of atoms that did that. So the question is, how many atoms is that? How many atoms of hydrogen does it take so that collectively they have the same mass in grams that one atom would have an AMU? And I'm not going to go through how we do that. That's a whole different ball game. It's a whole discussion of how do you actually do that experiment. But the point is it can be done. And that leads us then to a very practical result. We're going to define something as called the molar mass. Molar mass, okay? And the molar mass is equal to the mass of a substance when we have 6.022 times 10 to the 23rd of that substance. It turns out that the number of hydrogen atoms it would take to give you 1.00794 grams is approximately this number. This is an estimate, right? So, you'll see this number in ALEKS out to like 7 or 8 significant digits. I'm only writing it out to 4, but look, it's a big number, right? And that is often referred to as Avogadro's number. If I could spell Avogadro the first time around, that would be great. Avogadro's number. Well, that's what they called it when I was growing up. Sometimes they call it the Avogadro number. It's not take the possessive out. It's not like he owns it or anything like that. And the symbol for that is typically a capital N. I can't claim it's always that because not everybody uses the same convention, but typically it's a capital N with a subscript capital A. N sub A meaning the Avogadro number, Avogadro's number. And we define it as a mole. So here, after all this discussion, here's what the mole is. The mole is essentially a conversion factor from AMU to grams. If you take 1.00794 AMU and you multiply it by the Avogadro number, you get the number of grams. Okay? So if we have 6.022 times 10 to the 23rd hydrogen atoms, that's called a mole of hydrogen atoms. And the mass of that number would be 1.00794. Again, think about it logically, right? One atom weighs very little, 1.00794 AMU. You could figure out what that number is in grams. It would be a tiny number. It would be 10 to the minus 23 grams. But if I keep counting more and more and more, eventually I'll get up to 1.00794 grams. And that's because I have this many hydrogen atoms, 6.022 times 10 to the 23rd. The same is true for any other element. So if I take, for example, element number 6, which is carbon, one carbon atom, right? One C atom carbon is 12.0107 AMU. If I have 6.022 times 10 to the 23rd carbon atoms, that would be 12.0107 grams. Sorry, G for grams. Okay. This is more practical for us than this is. We could use it, and there are certain problems where you might use that, but we live in a macroscopic world, right? We don't eat an atom at a time. If you said, hey, give me a molecule of sugar or give me a molecule of coffee, it's not really possible because coffee has all kinds of molecules and different molecules. We wouldn't be very happy. We wouldn't even be able to taste it. But if you give me 6.022 times 10 to the 23rd glucose molecules, sugar molecules, or caffeine molecule, well, that might even kill you. But different molecules, that many, a large number of those molecules, now you're in the macroscopic world. Now you're able to do things, okay? A mole is 6.022 times 10 to the 23rd of that substance. So if I have 6.022 times 10 to the 23rd hydrogen atoms, I have a mole of hydrogen atoms. The same goes for any of these elements. And the same goes for molecules, right? If I have the mass of a molecule and it's in AMU, if I have 6.022 times 10 to the 23rd of those molecules, the mass will be the same as it was in AMU. It's just the unit will be in grams now. And so that makes it very useful. Okay. So there you go. That's the sort of background on this. Now what I would like to do, that only took me 20 minutes, is to show you a problem. Okay. So there's our number. I do want to warn you that the Avogadro number, I'm only writing it out to 4 significant digits here, but Alex, the one when you get in the, when you did the original tutorial to register, they actually had you click on N sub A, Avogadro's number, and it was 6.022, blah, 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 blah. And so that you want to use the number that they have in their little table there, their data table. Okay. Otherwise, it will start telling you you're wrong about certain problems, and that can be really annoying. Okay. Let's see. Let us share this one right here. There we go. Now, in a way, this is a bit of an awkward problem. It's not a type of problem I would have designed, but it does make you think about things a little bit. And let's take a look at it, okay? Now, a lot of this problem is really dealing with unit conversions of the metric prefixes, the SI prefixes, we call them, like milli, kilo, that sort of thing there. In fact, there's milli in here as a prefix, and there's kilo in here as a prefix. So let's read the question first, and then we'll take a look at it using the Avogadro number. A raindrop has a mass of 50 milligrams. Now notice on Alex, they put a decimal point after whole numbers. So like if you have a number like 47, they'll put a decimal. I've never seen people do that on purpose all the time, but they're trying to be consistent. So they ask that you do that. So if you come up with a number like 37, just write 37 decimal. So a raindrop has a mass of 50 decimal milligrams, and the Pacific Ocean has a mass of 7.08 times 10 to the 20 kilograms, right? Use this information to answer the questions below. Be sure your answers have the correct number of significant digits. So they're not really, oh, actually they do tell you. The first one, it says, what is the mass of 1 mole of raindrops in grams? They're telling you the units. And then they say round your answer to 2 significant digits. Okay, so they're telling you 2 significant digits. So if you end up with 37, you would write 37 decimal grams. In the second question, they ask you how many moles of raindrops are in the Pacific Ocean, which is an interesting question, right? Like how many raindrops are in the Pacific Ocean? How many moles of raindrops are in the Pacific Ocean? Answer your, round your answer to 2 significant digits. I don't know offhand. I mean, 37 might be the answer. There might be, in terms of the number of moles of raindrops, it might be like, 10 moles or 100 moles or 1,000 moles, but I'm not sure. It actually might be, well, we'll see. Let's go through it, okay? So let's take a look at the numbers that they're giving us. They're telling us there's 50 milligrams per raindrop, 50 milligrams. And then the Pacific Ocean has the mass in kilograms. The first question is, what's the mass of 1 mole of the raindrops? Okay, so that in a way is the easier part. Okay, so the idea here then is you got this little raindrop. I'm not good at drawing raindrops, but you got this little raindrop, and the mass of that raindrop is 50 milligrams. Okay. And then you've got this Pacific Ocean. It's going to have a lot of raindrops in it, right? And that's where the rain comes from, right? It comes from things like the ocean and lakes and rivers. It comes from the water that's either on the ground or in the water. Evaporation, right? Essentially, the sunlight evaporates the water from the surface. So this is your Pacific Ocean. It's got a lot of raindrops in there, right? The Pacific Ocean is huge, a lot of raindrops. Okay. Now, they give us the mass of the Pacific Ocean. The mass here is 7.08 times 10 to the 20 kilogram. Now, I'm not sure what's the mass of the Earth is. Isn't the mass of the Earth 10 to the 24 kilo? It must be 10 to the 27th kilograms or 10 to the 28th kilograms, because the Pacific Ocean doesn't weigh as much as the Earth. That's for sure. Okay, I'll have to check that. So that's how much that weighs. So notice this is in milligrams, right? This is called a milligram. mg. Those are used in the medical field, right? A lot of times we do milligrams. This is a kilogram. This is used in physics a lot, in engineering. If you go to the gym, very often the weights now are in kilograms. A 45-pound plate is around 20 kilograms. Okay. So we have, in terms of mass, different units, right? So if I gave you a question where I said, the weight of this apple, and I gave you the mass in ounces, and the weight of this watermelon, I gave you the mass or the weight in pounds, you would realize, well, you can't just add ounces to pounds. You can have mixed numbers, I guess, but generally if we're going to add things or subtract them, we want them to be in the same units. Okay, so let's talk about doing that right now. What I'm going to do is I'm going to convert these to just grams. That way they're both in the same units. So we want this one in grams and we want this one in grams. Okay. It's not the only way to do it. You could convert the kilograms to milligrams, or you could convert the milligrams to kilograms, but it doesn't really matter. We just want them to be in the same unit. It is useful when you're doing chemistry calculations to have things in grams. It's more useful than kilograms, except there's exceptions to that, but generally we want them in grams. The molar mass, right? So the molar mass is like per mole. It's 1 mole of a substance. Okay, the mass of 1 mole of a substance. So let's do the conversions here. So these are some of the metric prefixes, SI prefixes you should know. I'm going to start with the smallest one. You're not going to use this very often, but it's probably good to go through it. Here's atto. It's a lowercase a, and that's 10 to the minus 18. So that's the meaning of atto, or a is a abbreviation, 10 to the minus 18. Femto, which is an F, 10 to the minus 15. Pico, lowercase p, 10 minus 12. Nano, lowercase n, 10 to the minus 9. Now here's an interesting one, micro. Micro is not an English letter. It's a Greek letter, mu. It's called mu, M-Y-O-O, mu. And this is 10 to the minus 6. So you'll see this quite a bit, micro. Oh my goodness. Apple pencil. Okay. Milli, smaller m, 10 to the minus 3. Centi, c, 10 to the minus 2. Deci, d, 10 to the minus 1. Okay. So those are all the small ones. Like when we weigh things that are small, like a raindrop, we tend to use these smaller ones, and they actually go out smaller. There's zepto, for example. Now let's do the bigger ones. So I'm going to start with kilo. There's a deca and a hecta. I'm not going to worry about that. We don't use those very much anymore. So there's kilo. Kilo is 10 to the 3. And actually, I forgot to put the abbreviation. Sorry. K, 10 to the 3. Mega, capital M, 10 to the 6. 10 to the 6. Giga, capital G, 10 to the 9. Tera, capital T, 10 to the 12. And again, they get bigger as well than that. There's 10 to the 15, 10 to the 18, 10 to the 21, 10 to the 24. I'm not going to go over those ones. I'm just showing you the most common ones here. Okay. So notice we have one of them here, kilo. That one's used here. And then we have milli. That's this one right here, right? So I'm going to convert them both into grams. So here's how we'll do it. 50 milligrams. That's what we were told, right? Okay. Now there's a couple ways to do this. One way is to use the definition of what a milligram is. A milligram is one milligram is 1 times 10 to the minus 3. Millis 10 to the minus 3. Okay, so 1 times 10 to the minus 3 grams is 1 milligram. So I'm going to use dimensional analysis. Look what happens. The milligrams divided by milligrams is 1. So you see what I'm doing? I'm multiplying it by the number that represents the prefix and then the unit, which is grams, divided by the name of the prefix, or the name of the prefix with the unit, okay? 1 milligram is 10 to the minus 3 grams. And the one you put on the numerator, the one you put on the top, is the one such that when you multiply all the units, let me show you multiplying through all the units here. Milligram times grams over milligrams, right? That's really what I'm doing. I'm multiplying by grams over milligrams. So the milligrams cancel and you just got grams, okay? So then enter that into your calculator or just move the decimal point 3 places and you'll get 0.050 grams, okay? 50 times 10 to the minus 3 times 1 times 10 to the minus 3 is 0.050. And that would now be in grams. Now let's do the same thing over here. We've got 7.08 times 10 to the 20 kilograms. We want to get rid of the kilograms and convert it to grams. Kilo is 10 to the 3. So since you're trying to get rid of this unit here, you want to put the kilo at the bottom, 1 kilogram. Okay. And that would be 1 times 10 to the 3 grams. So again, take a look at what I'm doing. I'm taking the number here. Oops, sorry, not that one, this one. And I'm putting that up here in grams, and that's equal to 1 of these kilos, because a kilo is the same thing as 10 to the 3. Really what you're doing when you multiply by that ratio is you're just multiplying by 1. It doesn't seem like it, but 10 to the 3 grams is the same thing as a kilogram. So in a way there, it's like you're multiplying it by its identity. You're just changing the units though. Okay. The gram, I'm not claiming a gram is the same as a kilogram. I'm claiming 1,000 grams is the same as a kilogram. Okay, so that's going to get larger, right? That's going to increase the value, and it's going to be 7.08 times 10. Now here's a nice little thing about exponents. If you have the same base, 10, right? 20 and 3, you just add them. So if you're multiplying two numbers together and you have exponents and the exponents have the same base, 10 to the x, right? Then you can just add the numbers. If you're dividing, you can just subtract them. But if you're multiplying, you can just add them. So 20 plus 3 is 23. Very cool. Now the grams are here. So now they're in the same unit. So that's the mass of the Pacific Ocean, and that's the mass of a raindrop, right? Okay, so let's get back to the question. What is the mass of a mole of raindrops? Well, that's easy, because we know what a mole is. So the mass of 1 mole of raindrops, well, a mole is, sometimes it's abbreviated MOL, 6.022 times 10 to the 23rd. So if we're talking about raindrops, it would be 6.022 times 10 to the 23rd raindrops. Okay, that's how many it would be. So let's do this. 50, oops, that was in milligrams. 0.050 grams times 6.022 times 10 to the 23rd. And that'll give us the number of grams in 1 mole, because a mole is 6.022 times 10 to the 23rd. Now, let me be technical about the units. That's how many are in 1 mole. 6.022 times 10 to the 23rd raindrops is 1 mole. Okay, like a dozen. A dozen is 12, right? A mole is 6.022 times 10 to the 23rd. All right, I don't know what I did with my calculator, so let me bring out the phone then. We'll use the phone. Okay, so 0.050 times 6.022 times 10 to the 23rd, and you get 3.011 times 10 to the 22. Now, how many is grams per mole? You know, that's very interesting. That's a molar mass. We just figured out the molar mass of raindrops. Now, molar mass is used in chemistry. It's not used in meteorology, but that's really the molar mass of raindrops. If raindrops were an element in the periodic table, or if they were a particular compound, like, you know, a raindrop is a compound or a molecule, then that would be the molar mass. Okay. Okay, so that's how many grams are in a mole. Now, let's ask the following question. Part 2, sorry, let me read it again. How many moles of raindrops are in the Pacific Ocean? By the way, it's said to round it to 2 significant digits. So I just did there, right? 3.0 has 2 significant digits. Okay. So this is 1 mole. 1 mole of raindrops has a mass of 3.0 times 10 to the 22 grams. Okay. So now, how much does the ocean weigh? So really what we're doing is we're going to say, hey, there's a mole right there. There's a mole right there. I'm just like counting the number of moles of water, of raindrops in the ocean, right? A mole of raindrops is one of these little circles I'm drawing. There's another mole. There's another mole. How many are in there? So what you do is you say, hey, you got your ocean, and it's 7.08 times 10 to the 23rd grams, okay? And what you can do is now you can say that 1 mole of the raindrops, notice I took the E off the mole, which is fine. 1 mole of raindrops is the same as 3.0 times 10 to the 22 grams. Now I'm going to leave the 011 because this is we did an intermediate step. So times 10 to the 22. So I'm using that original number I calculated there. And the grams are going to cancel, right? And you just got moles. You have moles of raindrops. Okay. I'm just portioning it out. So now, actually, the number looks like it's going to be pretty reasonable. It might be like 20 or something like that. 7.08 times 10 to the 23 divided by 3.011 times 10 to the 22. It's like 23.51. So I'm going to round it to 2 significant digits. So that's 24. Remember to put that decimal point. 24 moles. So actually, it's like kind of interesting, right? The number of moles. So you do these sorts of calculations, you end up with these interesting things. That's a pretty, you know, like counting number, 5, 10, 15, 20. We got about 24 moles. I was kind of estimating the other day, thinking about the number of stars in the universe. A galaxy has about 1 trillion stars. So that's 10 to the 12th. Well, some people say it's 100 billion, but every 5 or 10 years, they increase the number by some amount. So let's say it's 100 billion. That's 10 to the 11th. And then they say the number of galaxies in the universe is also 100 billion. So that's 10 to the 11th. Again, I think that number will go up in time. But if you then multiply together 10 to the 11th times 10 to the 11th, you get 10 to the 22, right? You add the exponents. You get pretty close to a mole, right? 10 to the 6 times 10 to the 23rd. So if they at some point say, well, actually, it looks like there's, you know, 400 billion stars in the Milky Way. And it looks like there's more, there's James Webb Telescope is going up there. They might be able to get a better estimate of how many galaxies are out there. Maybe it's not 100 billion, maybe it's 600 billion, Then you start getting up to, 6 times or 2 times 10 to the 23rd, right? So you're getting pretty close to a mole. So for me, I think it's probably not unreasonable to say that the number of stars in the universe is probably about a mole, right? And likewise, the amount of raindrops in the Pacific Ocean, the largest ocean in the world, is about 24 moles, right? That's about what it is. So there you go. So there is this idea of the mole, okay? There's so many different types of problems you could ask about the mole, but that was one of them. I wanted to show you that one. So let's take a look here. Oops, sorry. All right, let me close that one. Okay. So let me show you this one. This is an interesting problem. It's pretty simple, but I want to show it to you. I don't recall actually talking about it last semester. So let me show you. Remember, what you're doing in the lecture component is you're just solving problems, right? That's the primary thing that you're doing in this course is solving problems. So here's one. This says finding the chemicals. Again, still section 3.4. Finding the chemical formula from a mole ratio. So an unknown compound has the following chemical formula, PbOX, where X stands for a whole number. Generally speaking, when we write out the chemical formula for a compound, it will be all whole numbers. We wouldn't have PB 0.7 or PB 1/2. It's going to be whole numbers 1, 2, 3, 4, 5. There's some exceptions to that. There are substances out there. There's some famous copper oxide superconductors that have fraction like 2.7 or something like that. But we'll stay away from those. So there it is, PbOX, where X stands for a whole number. Measurements also show that a certain sample of the unknown compound contains 7.3 moles of oxygen and 3.6 moles of lead. Write the complete chemical formula for the unknown compound. So here it is. We want to know the chemical formula. They give us some numbers here, but see how they're not whole numbers? We want them to be whole numbers is the point. Okay. So let me show you how to deal with that. So we got PbOX. And X is going to be a whole number. What that means is it's either going to be 1 or 2 or 3 or 4. It's probably not going to be any larger than that. If it's a 1, we don't write the 1. It's just inferred. So you would just write PbO. If it said PbO, that would just mean that there's 1 oxygen and 1 lead. Okay. So then they tell us that we have 7.3 moles of oxygen. And we have 3.6 moles of the lead. Okay, so this is a very simple problem, but I wanted to show it to you. Again, because I don't think I did it last semester, so it may not be in that previous video, but it's also useful for us. The compound is going to have a whole number ratio. And generally what we look for, particularly if there are metals involved, is we look for the whole number ratio, 1 to 2, 2 to 1, 3 to 2, 4 to 5, that sort of thing, okay? Sometimes it can go up pretty large, but generally they're pretty small numbers. Particularly with the metals. The metals, it's unusual to see more than 3 or 4 atoms in the formula. So you're not likely to see like PB7 or PB17. It's possible maybe, but not likely. So here's what I would recommend doing. Really what we're doing is we're just trying to find the ratio. See how that's a 7.3 and that's a 3.6. Just take the 7.3 moles of oxygen and divide that by this. So take the larger one and divide it by the smaller one, 3.6 moles of lead. And if you do that calculation, I'll do it on my calculator, but I already know what it is. You get 2.0277 repeating decimal, okay? That is pretty close to 2. So really what that means is there's twice as much oxygen in terms of the number of moles in the compound relative to lead. It's like a 2-to-1 ratio, right? So this ratio of 7.3 to 3.6 is the same as the ratio 2 moles of oxygen for every 1 mole of lead. So that's why they didn't put a number here. It's just PB, meaning 1, right? So that means it's 2-to-1. And what's the meaning of that in terms of the formula? That means it's PbO2, right? 2 goes there and the 1 goes right there, okay? Now, if they had, well, I'm not gonna go on there. There you go. That's pretty much how it works. Now, let me, just to be cautious about this, I wanna see if there's any that are a little bit more complicated. Sometimes there are. 8.4. So really what you're doing is you're just taking the ratio, take the larger divided by the smaller, and the lesser, the greater divided by the lesser, and then just round it essentially is what you want to do, okay? And then that should work. So it's, again, it's not a particularly difficult problem, but it's one I wanted to show you, okay? Let's see here. Interconverting. Let's take a look at this one. So this one is not, this one right here just involves a lot of not steps, but like a lot of little numbers to calculate here. So let me show you this one here. Again, I don't think I did this one last semester for the students then, so I'll show it to you here. Interconverting numbers of atoms and mass of the compound. Again, still section 3.4. Calculate the number of nitrogen atoms in a 70.0 gram sample of dinitrogen tetraoxide. See the di and the tetra? Di means 2. Mono is 1. Di is 2. Tri is 3. Tetra is 4. Penta is 5, like pentagon. Hexa, hexagon is 6. Hepta is 7. Octa, Doc Ock from Spider-Man, 8, right? Octa is 8. Nona is 9, and then deca is 10. So dinitrogen tetroxide is N2O4. Be sure your answer has a unit symbol if necessary, and round it to 3 significant digits. So 70 grams of N2O4, how many nitrogen atoms? Now, be careful. Write this number down. How many nitrogen atoms in this sample? So imagine it this way. You've got this sample, and how much does it weigh? You put it on a balance, and you find that it weighs 70.0 grams. Okay, so there's a bunch of molecules in there, but look at it. Look at the formula, N2O4, right? So N2O4, I'll draw it this way first. N2O4 most likely has 2 nitrogen atoms bonded together. We'll get the bonding later in the course. Don't ask questions about electrons and electron orbitals till we get there. That's later. So there's your N2O4, right? You have 2 nitrogens. This molecule is actually pretty unstable, and it'll break up into 2 NO2s, 2 separate NO2s. But there's N2O4. Typically, we actually draw it this way. I think that's a bad way to draw it. Let me do it this way. N2O4, like that, right? Okay. All right. So how many nitrogen atoms? So notice there's 2 nitrogen atoms in each molecule, right? There's 2. That's the meaning of the N2O4. So this is what I'm going to do. Here's my strategy. Very common type of problem. You take the mass and you convert that to moles. Okay. How do you do that? How do you convert the mass of something to moles? You divide by the molar mass. Okay. If you divide the mass of something by its molar mass, you will get the moles. Then in the second step, what we really want to do is we want to convert it to the number of atoms of N. Okay. How many atoms of N are there? Okay. Now, what I'm going to do is I'm going to note that if you have a mole of substance of a substance and you want to find out, actually, let me change this a little bit. Let's do molecules. This will be a little bit more clear of N2O4. If you want to go from moles to molecules, you multiply by the Avogadro number. Okay, so I'm just writing that above the arrow, times 10, 6 times 10 to the 23rd. Okay, so to go from mass to moles, you divide by the molar mass. To go from moles to molecules, you multiply by Avogadro's number, because remember, a mole is Avogadro's number of that substance. Now that's going to give you how many N2O4s you have, but in this question, there's one more step you got to do. So you might find if you don't do this step, you'll be off by a factor of 2. There's 2 nitrogens for every molecule. So there's 2 atoms of nitrogen divided by 1 molecule of N2O4. It'd be like if I said I have 1,000 bicycles, how many wheels do I have? Oh, good job, you calculated the number of bicycles, but you got the number of tires wrong. You got the number of wheels wrong. Why? Well, you didn't multiply by 2. You had to multiply by 2 because there's 2 wheels, 2 bicycle tires in 1 bicycle. Same here. If you find the number of molecules of N2O4, you just got to multiply by 2 to find the number of atoms of nitrogen. Okay. So what's the molar mass? Oh, that's easy. You go to the periodic table and you look up the atomic masses of each element. Actually, I think that number is wrong. I'm just going to put 14.01. Oh, I'm sorry. I have the periodic table right here. I did a couple of minutes ago. What did I do with it? I'm so sorry. That's a very strange thing that I just had to fill 1 minute ago, half an hour ago. I can't find it now. Okay, that's fine. So let's just use 14.01. I do have it on my phone. You can get a periodic table on the phone. So let's look it up here. Periodic table, nitrogen, 14, a lot of information in there, 14.0067 grams per mole. So 0067. So let's write that. Let's use it. And then oxygen, I know oxygen. I do that one so often. 15.9994. There we go. Okay. All right, so let's do the molar mass. The formula is N2O4. So there's 2 nitrogens. So 2 times 14.0067. The units of molar mass are grams divided by moles, grams per mole. That's how much 2 nitrogen atoms, 2 moles of nitrogen atoms weighs in grams. 2 times 14.0067 grams. Plus 4 oxygen, so 14 times 15.9994. Again, the units is grams per mole. It's AMU if we were just doing a number of atoms. If I just said there's 2 nitrogen atoms and 4 oxygen atoms, but this is the number of moles we're doing. We're doing the molar mass. Remember, the molar mass is the mass of 1 mole of a substance. So 2 times 14.0067 plus 4 times 15.9994, and you get 92 This one goes 4 digits past the decimal point, so is this one. 0.110 grams per mole. Okay, so there's your molar mass, right? Relatively simple. You look at the chemical formula, you look up the masses of each individual element, you take the subscript, multiply it by the mass of that first element, add that to the subscript of the second one times its mass, and then if there's 3 or 4 elements, you just add them all together, okay? Now, what I said was, if you want to go from mass to moles, you divide by the molar mass. So let me show you how I do that. We've got 70.0 grams of N2O4. Notice I'm going to be really careful here about putting the units in. I'm very explicitly. N2O4, number of grams of N2O4. Divide by the molar mass. Now, let me show you why it's divide. The reason it's divide is if I write this as, I'm going to take this over here, 92.0110 grams equals 1 mole. That's really what that means. 1 mole weighs 92.0110. So they're equal to each other. So I'm going to divide. What that means is I'm going to take the number here in grams and put it in the denominator. And I'm going to be, again, very explicit here. 1 mole of N2O4. So that's what I mean by divide. What I mean is take the number that's there and the unit that's in the numerator, and that goes at the bottom. You're dividing by that. The one that's in the denominator, that's going to go in the top. So 1 mole of N2O4. Okay. So 92, okay, so now I got to go here. 70.0 divided by 92.0110. And you get 0. Looks like there's 3 significant digits, but I'm going to do one extra. 0.7608. And what are the units going to be? Grams of N2O4 are gone. You've got moles of N2O4. Okay. The reason I kept 1 extra digit, see there's 3 digits here. So you would think, oh, it's multiplication division. So you just have 3. Is that we're going to use this number in another step. If you're going to use an intermediate value in the next step, what you do is you take at least 1 extra digit. So the 8 is the extra digit, and just put a line over the one that you know you need to round to. Eventually, you got to round to 3 significant digits here. Okay. Now, step 2, it's really step 3 because first was finding the molar mass. Now we divided by the molar mass. Now we're going to multiply by Avogadro's number. If you have the mole of something and you multiply by Avogadro's number, that gives you the number of them. Like if I say I have 1 dozen eggs, multiply it by 12, now you know how many eggs you have, right? A dozen isn't like a, I mean, a dozen is a thing, but it's not the number. It's a unit, the dozen. But if I have a dozen eggs, that means I have 12 eggs. 12 is the number. So we're trying to find the number of atoms. So multiply by 12 to get the number of eggs. But here we're going to multiply by this much larger number, Avogadro's number. So 0.7608 moles. I'm going to put that line there to remind me that we got to round it to 3 significant digits. 6.022 times 10 to the 23rd. And again, the units is, this is a number, it doesn't have a unit, but it's per mole. The mole is the unit. So it's no units over moles. So the unit is 1 over moles. So now this is N2O4. So that's going to cancel. And that's going to give you the number of molecules of N2O4. And you get, again, 4.581, but we want to round it to the 3rd digit, times 10 to the 23rd molecules. Okay, so divide by molar mass to get moles. By the way, if you had moles and you wanted to get the mass, you would multiply by the molar mass. You just go the opposite direction. Now you got the number of molecules of N2O4. Let's make sure that we're really writing this down. This is N2O4. But now let's come back to the number, the question. The question is how many nitrogen atoms? And that's where the bicycle analogy comes in. If I said there were 4.581 times 10 to the 23rd bicycles, how many tires are there? You would multiply by 2. So 4.581 times 10 to the, 23 molecules of N2O4. And then I'll write it out as 2 atoms of nitrogen per 1 molecule of N2O4. Okay, I'm being really, really a stickler in doing this, but I want you to see the dimensional analysis, how that works. So mathematically, you're just multiplying by 2. And you're going to round it. 9.163 times 10 to the 23 atoms of nitrogen. There's our answer. But how many significant digits did Alex ask you to do? They said round it to 3 significant digits. So I'm going to do that. 1, 2, 3. So let's just do it this way. Get rid of this one right there. There's your 3 digits, right? I just got rid of the 4th digit because it was less than 5. So 9.16 times 10 to the 23rd atoms of nitrogen. Okay. So there you go. There's your section 3.4. I did miss a couple of lectures, or at least, yeah, I missed a couple of lectures at the beginning of the week. So I'm going to do a little makeup lecture tomorrow, which is Friday, where I'll talk about stoichiometry. So section 3.6 and 3.7, I'll talk a little bit about it. Okay. So take care. Reach out to me if you have any questions, and I hope you are having a good day. Bye-bye.